Now we move into the next video, which talks about properties, the idea being that the stronger the interparticle force, the harder it is to break them, thus the harder it is to melt a particular solid. And this was where we also brought in hydrogen bonds, which of course is an extremely important A-level topic. As heat is added to the system, what occurs from point A to point B? Well, we're starting off at low temperature, so presumably we're starting off with a solid. And as you heat up a solid, it gets hotter, so the temperature rises until you get here to the melting point. At this point, all of that solid has to be turned into a liquid, so that requires the heat going in to modify the intermolecular forces. So this plateau here is as we go from solid to liquid. And by this stage, all the solids turned into liquid. So now what we're doing is we're just heating up a liquid, so that liquid gets hotter until it gets here to the boiling point. Now at the boiling point, now you've got to break all of those interparticle forces to turn all the liquid into gas. And so this plateau here is associated with the liquid going to the gas until now all the substance is gas. So you keep heating it up, you just get a hotter gas. So therefore from A to B, this corresponds to turning the liquid into the gas, otherwise known as the liquid is boiling. Various heats of water in order of decreasing size, so heat of fusion, heat of sublimation, heat of vaporization. Well, fusion is of course solid to a liquid. That's where we're sort of stretching those interparticle forces. Vaporization is liquid to the gas. That's where we're breaking those interparticle forces. And sublimation is going from the solid straight to the gas. So going from the solid to the gas is equal to solid to liquid plus liquid to gas. Thus the heat of sublimation is these other two put together. Thus it must be the biggest. Okay. As far as the other two, solid to liquid, as I say, we're stretching the interparticle forces. Liquid to gas, we are breaking the interparticle forces. Harder to break than it is to stretch. So therefore the heat of vaporization is the middle one and the heat of fusion is the smallest one. Just like we say there, heat of sublimation biggest, heat of vaporization in the middle, heat of fusion smallest, stretching, breaking, both put together. For solid substances of the same approximate molar mass, the lowest molar heat of fusion is expected for, well, the lowest molar heat of fusion is going to go for the weakest IMF. So let's have a look at which of these is the weakest. Ionic bonds, nice and strong. Metallic bonds, pretty strong. Network covalent, nice and strong. So it's between the polar and the non-polar. And of course, polar with the dipole-dipole, much, 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 much stronger than the poor little London dispersion, otherwise known at A levels as the van der Waals forces. So therefore the lowest molar heat of fusion will come for the non-polar covalent substances with those really weak, pathetic London dispersion forces. So later members of group 6A chalcogens form hexafluorides, SF6, SEF6, TEF6. Given temps, one's a solid, one's a liquid, one's a gas. Well, if it's a solid at this given temperature, that means it has neither boiled nor melted, so its melting point and boiling point are higher than this given temperature. If it's a liquid at this temperature, that means that it's melted but not yet boiled. So in other words, its melting point is lower than this temperature, but the boiling point is higher than the temperature. And finally, of course, if it's a gas, that means it's melted and boiled, so its melting point and boiling point are lower than the given temperature. Now, by and large, the melting and boiling points, of course, depend on how strong the interparticle forces are. So the one in red that's still a solid is going to have the strongest intermolecular forces. The one that's liquid is going to have the medium ones. And then the one that is in green here, the gas, will have the weakest intermolecular forces. Now we know, of course, that similar molecules, the ones that have the higher mass have the higher intermolecular forces and thus the higher boiling points and melting points. So essentially what we're saying here is that this one is the heaviest, this one is the middle, and this one is the lightest of these. Now, of course, this only works if you don't change your intermolecular force type halfway through the series, but these are all nice little octahedral species. Okay, so the heaviest one is, of course, TEF6, so that makes that solid. And therefore, the middle one is SEF6, which makes it the liquid. And finally, the lightest one, SF6, so that is the gas at this given temperature. Which of ethane and ethanol experience London dispersion in solid and liquid? Well, ethane is, of course, that nice hydrocarbon. It is a non-polar covalent molecule, thus it experiences and only experiences a London dispersion, which of course at A level you're calling van der Waals anyway. Ethanol, CH3CH2OH. Well, that OH there tells it all. It makes it a polar molecule, but you've also got the OH there so it can hydrogen bond. But of course, as well as hydrogen bonding, it also has London dispersion because everything has London dispersion forces. So therefore, the correct answer to this is both. Ethane only has London dispersion, ethanol has London dispersion, and hydrogen bonding. Which following correctly is compounds order of increasing strength of intermolecular forces. So what we have to do here is we have to assign the intermolecular forces and then know which are strongest. And of course, I'm going to have a London dispersion. I'm going to have dipole-dipole. I'm going to have hydrogen bonding in that order. And then, of course, once you've got similar type species, then the important thing becomes mass generally. So first one, H2S is a polar molecule, just, so therefore I have dipole-dipole. Water, of course, has hydrogen bonding, and NO is a polar molecule, so therefore it will have dipole-dipole. So thus we don't have increasing strength here because we got hydrogen bonding smack in the middle of two dipole-dipoles. Hydrogen bonding will be stronger. CH3CH3, London dispersion. CO2, London dispersion. CH4, London dispersion. CH4, London dispersion. H2S, dipole-dipole. NH3, of course, has the nitrogen-hydrogen bonds, thus hydrogen bonding. And then finally, NH3, hydrogen bonding. HF, again, fluorine, very electronegative. H bonded to F involves in hydrogen bonding. And H2S, as we already said, dipole-dipole. So therefore, the one that has increasing strength and intermolecular forces is very obviously C, where you go London dispersion, dipole-dipole, and hydrogen bonding. Which of the following has the lowest boiling point? Well, these are all hydrogen bonded to halogens, therefore you would immediately say they have dipole-dipole. But when you have similar dipole-dipole series, well then you still look at the weight, and so the size increases as we go down. So therefore you would expect the boiling point to increase as you go down, because fluorine is so small, then chlorine, bromine, iodine, astatine, really, really big. And that would be true. Similar molecules increase their intermolecular forces based on mass if it were not for the fact that you're actually changing the intermolecular forces as you're going through this series, because of course fluorine is the most electronegative atom. Therefore HF will have hydrogen bonding. So what you've actually got here is that HF has the strongest intermolecular forces, which means we have to remove it from the series. Thus HCl is actually going to have the lowest boiling point. Whether or not HF has a higher boiling point than HI and HAT, you can't tell yet. What you can tell for sure is that HF is well out of series because it has hydrogen bonding stronger than just a regular dipole-dipole. Which of the following substances should have the highest heat of vaporization? Well, as we look down the list, we see they're all covalent species. So therefore, what we've got to do is assign the intermolecular forces and pick the strongest intermolecular force. SiH4, absolutely nothing special about it, non-polar, and therefore London dispersion. NH3, you draw it like this, got that lone pair, which makes it a polar molecule. So you'd say dipole-dipole, but then of course the more astute of you would recognize that any time you have hydrogen bonded to oxygen, fluorine or nitrogen, as we have here, you have hydrogen bonding. HCl right there, nice polar molecule, so dipole-dipole. pH3 got a lone pair, so you'd say polar molecule, so dipole-dipole. Actually, phosphorus and hydrogen, pretty much the same electronegativity, so this would not be a polar molecule, simply because all the atoms have the same electronegativity, but that's beyond the A level to recognize as far as we're concerned here. Lone pair distorts the geometry, so polar molecule. H2S, again, 2 lone pairs distorting the geometry. Sulfur definitely more electronegative than hydrogen, so polar molecule, thus dipole, dipole. So therefore the one that's going to have the highest heat of vaporization will be the one with the strongest interparticle forces. That is, of course, ammonia. And not only that, but would also have the highest heat of fusion, the highest melting point, the highest boiling point, and would have the lowest vapor pressure of all of these substances because it has the strongest interparticle forces. So which of the following should have the highest boiling point? Well, what we do here is look first of all at the intermolecular forces. Silicon dioxide, you need to know, is network covalent along with diamond and graphite. Argon is an atom, so cannot be anything but nonpolar, so London dispersion, Van der Waals field. CO2, of course, nonpolar molecule, so London dispersion. Mercury is a metal, so it has metallic bonds. H2O has hydrogen bonds. Network covalent, very, very strong. London dispersion, pathetically weak. Metallic can range from strong to very, very strong. Hydrogen bonding, I've put here as strong. Of course, they are strong compared to dipole-dipole or London dispersion. They're certainly not strong compared to ionic, metallic, or covalent bonds. Anyway, which of these is going to be the strongest? Well, the network covalent, very, very strong, so it will have the highest boiling point. Now, you should always be aware and think about regular knowledge because you don't need to know intermolecular forces to answer this. All you need to know is that silicon dioxide is sand, so it's a solid at room temperature. Argon, noble gas, so gas at room temperature. CO2, gas at room temperature. Mercury, you'll know, is a liquid at room temperature. And of course, water is a liquid at room temperature. So in other words, SiO2 is going to have the highest melting point. And thus you would assume highest boiling point because it's the only one that's still a solid at room temperature. Never be afraid to use general knowledge. Question 13, which of the following we expect to have the highest melting point? So again, looking for the strongest interparticle forces. So we'll assign the IMFs. When you've got CH3, CH2, CH2OH, you've got an OH in there. So hydrogen bonding. CH3O, CH3 is a polar molecule, so dipole-dipole. Pentane there is a hydrocarbon, so non-polar, has London dispersion. Then we've got OH, CH2, CH2OH. Well, we've got OH, so hydrogen bonds there, and CH3, CH2OH, again OH, so hydrogen bonds. So we can immediately eliminate second and third, but which of these three with hydrogen bonds is going to have the highest melting point? And the answer would be, you've got one OH to interact with butanol. We got two OHs with this ethylene glycol or ethane 1,2-diol, and then we got one OH with this one ethanol. So I would assume a molecule that has OHs at each end is going to have more hydrogen bonds, so we'll have the highest melting point.